Hello, statics class. This is the second of our equilibrium analysis examples. This is the second problem for February the 12th, 2019 winter quarter, Skagit Valley Community College. So for this example, we have a uniform density rod that is being held at the top of the pin. So the rod can rotate around the pin. The pin will not sustain any kind of moment. The rod has, again, it has a uniform density, and I think we're going to be given the weight, or we'll be asked to solve the problem in terms of the weight. But we know that whatever weight it has will, of course, act at the center of mass, which is halfway down the rod right here. Oh, 30 pounds. So it weighs 30 pounds. It's being held up by a wedge, which is being pushed with force P from right to left. And it's in equilibrium. So we're being asked, okay, what's the force P necessary to keep it in equilibrium? And for this problem, we are not considering friction. You can see it says negligible friction there. The rod length is 10 feet, and we're given some geometry here that this triangular wedge is 5 by 12. So that gives us this angle here, and most important, that's going to give us the angle of the normal force that will be exerted on the end of the rod, because of course normal force is always normal to the surface that is exerting it. So that'll give us a direction for the force that wedge will exert right there on the bottom of the rod. So there's no friction here, and there's no friction between the tip of the rod and the wedge. So basically all we have is the normal force of the wedge against the rod, the weight of the rod, and the pin. So for this one, we're going to end up using two free body diagrams to get to this. We're going to start with a rod, and then we're going to find the normal force between the rod and the wedge. That's kind of the connector between those two FBDs. And then we're going to use the free body diagram of the wedge to get us force P. So we start with the FBD of the rod. And again, this is a little bit of geometry here. So we've got the rod sitting at an angle theta to the vertical. And we were told back up in the problem description here that that was sitting at a 4 to 3 angle. So the angle is a tan of 3 over 4. So we can use that to calculate the force resultants in different directions. We have 30 pounds working straight down at halfway down the rod length. So that's 5 feet. The rod's 10 feet. So we have 5 feet from this point at A, where the pin is, to the effective application point of the rod weight. It's working through its center of mass. Since the fastener up at point A is a pin, we know that it can exert a vertical force, so we have that represented as AY, and a horizontal force, AX. So the only really tricky problem is getting the geometry of the normal force exerted by the wedge here with its geometry on the tip of the rod. And the key to that is remembering that, again, a normal force is normal to the surface exerting it. So it's not going to be angle theta here, it's going to be the angle phi that defines the wedge surface relative to our IJ coordinate system that's going to give us the direction of that. And I've represented that normal force as B. So equations of equilibrium, my little rod here is in static equilibrium, so the sum of the forces in the x equals 0, sum of the forces in the y equals 0, and the sum of the moments about any point are 0. So I can start adding all that up, and as usual, the most revealing equation is usually your moment equation. And so I'm gonna start with that one, even though the others definitely apply. It's going to be my moment equation usually that gives me the quantity that I need the fastest. But we'll just step through all the setups. First, made sure I knew what my angles were because I was going to use them. So I used arctangent of the 3 over 4 to get my theta, which is the angle that the rod is hanging with respect to the coordinate axes, and then phi, the 5 over 12. Here's my sum of the forces in the x. I have AX pointing in the positive I direction, and that's going to be opposed by the x component of my normal force down here, B, which is going to be cosine of 90 minus phi. Some little geometry there because we have it pointing up at 90 degrees to the surface. Here's the sum of the forces in the y. So I have AY at the pin, and I have it presumed to be pulling up. I don't know if it's pulling up. Probably is, but we'll find out. But I have it indicated as the y, as the positive y. So that's minus 30 pounds for the weight. And then because B is acting in the generally upward direction normal to that wedge surface, that's also positive, and it's going to be sine of 90 minus phi for the y component of B. So there's my sum of the forces in the x, sum of the forces in the y, and I took the moment about point A. I chose point A for a reason, because both AX and AY, which I don't know, are concurrent at point A. So if I take the moments about point A, I automatically take those out of the equation and make it far more likely that I'm going to isolate one variable and be able to solve it directly. So that there's some tricks to choosing where you're gonna apply your moments to make all of your linear algebra a little bit easier. So I ended up with merely by and bx in my moment expression, and because those are related geometrically by phi, I end up with effectively just b. Okay, we're coming back to our rod and wedge problem here. This is our second equilibrium analysis example. I have shifted the screen over to correspond to continuing parts of the solution in our second FBD. So the equations we're wrangling with here are continuation of the moment expression, which was the sum of the moments about point A, that top pin hanger on the rod. And you can see I have now substituted the geometry of our normal force for Bx and By. So now I have B times sine of 36.87 and B times sine of 53.13 as Bx and By, because it's just B directed along a given direction, normal force. And so that isolates B. I can solve for B, which now I could plug that back in to my free body diagram for the rod if I wanted to know, say, what the forces were up at the pin. But that's not what I wanted. I wanted to know something about the wedge. So I'm going to, forget about the pin for now. We don't really care about it in this problem anymore, even though we could solve for it. So I'm going to translate that B force down into a free body diagram of the wedge. So now I look down at the FBD of the wedge. So I've got its weight acting in the downward direction. I have a normal force coming from the surface it's sliding on acting upward. I have B acting kind of down and to the right at a known angle, because again this is 5/12, and then I have P acting to the left. Now, because I don't know how much the wedge weighs, I have no idea what the relationship is between N and W, because I don't know W. I do know that the Y component of B is, plus the weight is going to be equal to the normal force. I know that. So if this were a friction problem, that'd be great. I would need to know the weight, though, to understand the friction force, which would be presumably opposing P. But since I don't know that, it's not an issue. All I need to know is P. Lucky for me, there's only one other force component that's acting in the horizontal direction, and that's the X component of B. So all I have to do is, again, use the geometry of the normal to the surface, get a Bx, and say P equals Bx. And that's exactly what we did. I can write the equations of equilibrium for the Y. Can't solve them because I don't have W, but again, it's nice to know. But this is the one that gives me what I want. Sum of the forces in the x equals 0, so P equals Bx. I know Bx from the geometry that I already established earlier, and that gives me, I already know B from up here, so B is 14.06 pounds. And it is acting in the minus I direction, so it is pushing back, which is pretty much what you would think given the direction that the rod was pushing down. So there we go. One problem took two free body diagrams to get us the answer we wanted, one moment equation, and we're done. So that is it for our second equilibrium analysis example.